Reading the graph of f of x to find derivatives. Before we look at a graph of f of x to determine what the graph of its derivative, f prime of x, would look like, we want to look at the types of non-differentiability on a graph. So a function is not differentiable at a few different types of locations on a graph. So the first two I want to look at are at cusps and at corners. So remember that a derivative is the slope of a tangent line. So at this place right here, at this x value a, I cannot find a unique tangent line. So I would want a line that, first of all, just grazes the curve. So maybe we might think that this one would work and goes through the point, but what about this line here? So there's not a unique tangent line at a cusp, and similarly at a corner. So right here, this line or this line, there's too many different options. So at a corner or at a curve, so here at 0 or here at this location A, the function fails to be differentiable. So we would call that a place of non-differentiability. And there are two more locations where a function can fail to be differentiable. The next one is at a vertical tangent line. So if you notice this graph here, at this location marked as C, if I were to draw a tangent line, one that just goes through that one point near the point C and just sort of grazes the function, that tangent line would be vertical. And a vertical line has an undefined slope. Well, if the derivative is the slope of the tangent line, I can't have it be a non-real number because remember that a derivative is a limit. So at a vertical tangent, I would also say that my function is non-differentiable. And then finally, at places of discontinuity. So if we remember, differentiability, so I'm going to abbreviate this, implies continuity. And wherever you're discontinuous, you are also non-differentiable. So at any place of discontinuity, and remember those are jump, removable, infinite, and oscillating discontinuities, I would also not be differentiable at that location. So those are all the different ways that I can fail to be a differentiable function. Before we start looking at examples, we're going to define local linearity. So we say a function is locally linear at x equals a if the graph of that function looks more and more like a straight line as we zoom in on the point a f of a. And we want to define this term locally linear because if f prime of a exists, if the derivative exists, then f must be locally linear at that x value a. So if the derivative exists, then the function, when we zoom in really close on it, at that a value, it's going to have to look like a line. And so this statement tells us, well, if the function is not locally linear at a, so if I zoom in really close and it doesn't look like a straight line, then I know that the derivative does not exist. So it's because of this idea of local linearity that we know that derivatives don't exist at a sharp turn. So we're going to take a look at a graphing calculator for a second, and we're going to look at a function. So this function is x cubed minus x. And if I just move my trace button a little bit and I zoom in on just any random point, I'm just going to zoom in anywhere along this curve. So it still looks like a curve at this point. I'm going to have to zoom in just a couple times before it starts to look like a straight line. So I'm going to go ahead and trace again right about there. So I'm going to zoom in on that point. Alright, so I mean that's close enough. We could continue to zoom in and it would look like a perfectly straight line on the screen. As I just zoomed in closer and closer and closer, it would look like a straight line at this point. And that's because this the derivative actually exists at this value that I've chosen on this curve. As opposed to if I choose the absolute value of x, so let's go ahead and graph the absolute value of x, which we know, of course, looks like a V. If I were to zoom in now on 0, 0, where I know there's a sharp turn, so I'm right at 0, 0, and if I zoom in, whoops, let's try that one more time. If I continue to zoom in, there's really no amount of times that I can zoom in where at 0, 0, I'm going to look like a perfectly straight line. It's just not going to happen. So it's just going to continue to look like a V as I continue to zoom in over and over and over again. So since f is not locally linear, it doesn't look like a line near x equals 0, then f prime of 0 does not exist. So it's because of this idea of local linearity that sharp turns or cusps or corners are places of non-differentiability. Alright, now we're going to take a look at a graphical interpretation of derivatives given the original function f of x. So we did this a little bit earlier. We analyzed some piecewise functions where each piece was, for the most part, linear, and the derivative of a linear function is just the slope of the line. But we're mostly going to deal with curves, so let's take a look at this curve and consider it to be the original function f of x. So let's say this is the curve f of x here, and we want to analyze the derivative, or the slope of the tangent line at different points along this curve. So let's say we analyze the derivative, or the slope of the tangent line at this point here. So you'll notice that the tangent line has already been drawn for us. So the derivative at this point here would be some positive number, because this tangent line has positive slope. And in fact, anywhere over here off to the left, if I were to have picked another point and drawn a tangent line, that location is going to correspond to a tangent line with a positive slope, so that means that the derivative there will be a positive value. Up here, at the maximum of this particular function, if I were to draw a tangent line, that tangent line would be horizontal, as shown here. And horizontal lines have slope 0, so the derivative would be the value 0. And then anywhere over here off to the right of that maximum value, you'll notice if we draw a tangent line like the one at this point of tangency here, is going to have a negative slope. So the derivative at any location over here at any x value is going to be some negative number. Now what I want you to remember is that now we can find the derivative as a function. And if we can find the derivative as a function, we can graph that function. And so the reason we're analyzing the slope at these different points is because it's going to help us go from the graph of f of x to a sketch of the graph of f prime of x, the derivative function. So what I just said about the slopes of the lines at different points, we're going to summarize in the results below. So at a point x equals a on f of x, if the tangent line has positive slope, so at x equals a, then the derivative f prime of a is going to be a positive value and is going to be located above the x-axis on the graph of f prime of x. If the tangent line on f of x at x equals a has a negative slope, then the derivative at that point, so f prime of a, is going to be a negative value and is going to be located below the x-axis on the graph of f prime of x. And then finally, if the tangent line has slope 0, so it is horizontal on the original graph, then the derivative at that point, f prime of a, is 0. So on the graph of the derivative, it's going to be on the x-axis. So we're going to use this information to help us sketch the graph of f prime of x given the graph of f of x. Alright, so for this example, what we're being asked to do is match f of x to its derivative f prime of x. So you're going to have to do some labeling. This first row is graphs of f of x, original functions. So we'll call them a, b, c, and d. And we're going to match those graphs to their derivatives in the second row. So all of these are derivative graphs, which, let's remind ourselves, derivative graphs represent the slopes of tangent lines to f of x. So derivative graphs are slopes graphs. So we're going to keep that in mind as we analyze each function f of x. So we're going to look at a first, and we're going to notice that, well, a is a line. It's a perfectly straight line. So when we're thinking about slopes of tangent lines, well, this is a line already. So we can definitely find the slope because we have our tick marks here. So the slope everywhere is 1. I can see rise over run is just 1 over 1 each time. So this is in fact the line y equals x. And what I'm going to do is I move from left to right along this function. I'm going to, near the function, write a little 1. And that's to indicate the slope. So basically everywhere along this line, the slope is 1. And if I were to go attempt to find the derivative graph, well, what I'd be looking for is across every single x value, I want to make sure that the output is 1. So this is like a 7. Sorry, it's a 1. So that's going to match up with option number 3 in the second row. So across every single x value, the output, the function itself, is 1 every single time. It's a constant function 1 because as I look at the slope here, it's constantly 1 across this entire linear function. So that means that this is A. And then it gets a little trickier when it comes to curves. So let's go ahead and take a look at B, which is a curve. It's not a line anymore. And we're going to analyze the slopes of the tangent lines. Well, we don't have any tangent lines drawn on here, so that means we're going to have to just sketch little tangent lines to think about it. So I'm going to start on the left side. So as I move from left to right, I'm going to draw just a couple tangent lines. So let's say right here, I'm going to try to accentuate it. Let's say that's a tangent line to the curve. I'll draw another accentuated tangent line right about here, and then another tangent line. So I'm moving from left to right. Another tangent line right about here. So I cannot find the exact slopes of those tangent lines like I could for this linear function. But what I can tell is the sign, so whether these slopes are positive or negative. And I can tell whether the slopes are getting bigger or smaller as I move from left to right. So if I analyze this slope right here, if I were trying to numerically approximate it using rise over run, well, I'm going to fall, and then I'm going to run, and I'm going to fall quite a bit. So this is a pretty steep negative slope. So I'm going to put a big negative symbol right here. I'm going to try to make it pretty big. So this is a negative slope, and it's a pretty negative slope. So it's maybe like -10 is the slope of this little tangent line right at this point here. But as I move further to the right, as I move to this tangent line I've sketched, still negative, still a negative slope, but not quite as negative. So I'm maybe going to fall 5 and then run 1. So it's still a negative slope, but it's not quite as negative as this one. So I'm going to make my little negative symbol smaller. And then right here, maybe this slope is -1. It doesn't quite look even as steep as this one. So still negative, but not quite as negative. And then right when I reach this minimum value right here, so I would have a tangent line that is perfectly horizontal. So right here at the very bottom, if I were to draw a tangent line, apparently I can't draw a perfectly straight line horizontally, sorry. I would have a perfectly horizontal line if I could draw nicely, and the slope of a horizontal line is 0. So right down here at this minimum, it's not a sharp corner, it's a nice smooth curve at the bottom that's going to have a perfectly horizontal tangent line. I have a slope of 0. And then once I move just to the right of that, then I'm going to start to have positive slopes. So I'm going to go ahead and draw a couple tangent lines again and accentuate them a little bit. And I'm going to move to the right. So again, I'm moving from left to right, and I'm drawing myself a tangent line, something like that. And I can see that all of these slopes are positive, and this one, maybe the slope's +1. I can see it kind of looks like this line over here. So it's positive. I'm going to draw a little plus sign though, because this slope right here is steeper than that. Maybe I'd have to run, go up 3 and then over 1. So this is a little bit bigger and positive, and this one's definitely bigger. So it's definitely steeper, so I'm going to draw an even bigger plus sign. And so now what I want to try to do is match up to one of the graphs on the bottom row, given that I know the signs of the slopes. So I know that on the left side of 0, so over here on the left side of the y-axis, I'm going to have negative slopes. I'm going to need to be below the x-axis on the graph of my derivative, because that's where negative values live. And it's going to have really negative values the further left I am, and then it's going to have smaller negative values the closer I get to 0. So as I start to look, if I look at this first graph here on the bottom row satisfies what I'm looking for. As I think about being far on the left, I have some pretty negative values. So we can see this line here has some pretty negative values, and as I move to the right, they're still negative, but they're less negative. I'm getting closer and closer to 0. And right at 0, I wanted a perfectly horizontal tangent line with a slope of 0, so my slopes graph is going to have to go through 0, 0. So this graph satisfies that, and then just past 0, I'm going to have positive slopes, but positive slopes that get bigger. And so I can see that my slopes are now positive, so I'm above the x-axis to the right of 0, and my values are getting bigger as I move from left to right. So this is the graph of the derivative of b. So this first linear function is now the derivative graph of this second function here that we're looking at, this quadratic function, it's a parabola. So now let's go ahead and take a look at graph C. Remember, this is an original function and we're trying to analyze its slopes. And I'm going to start with a different strategy here. Although we can definitely move to from left to right, and that is a good strategy, what I want you to observe is that the 0 location, the place of horizontal tangency, was really helpful in figuring out which graph matched the function of the derivative. So I know that wherever I had a horizontal tangent line, I was going to have to go through the x-axis there. I was going to have to go through 0 wherever I had this place of horizontal tangency. So if I look at this curve here in graph C, and I think about any places where there'd be a perfectly horizontal tangent line, I'm looking for these nice little curved maximums and minimums. So I don't want sharp turns because I'm not differentiable there. But I can see that I would have a perfectly horizontal tangent line here and right here. So those slopes would be 0 at those locations. So in order to match this graph, I'm looking for a derivative graph that goes through the x-axis twice. I want 2 x-intercepts on the graph of the derivative. So if I look at what I have left, well, this option goes through the x-axis twice. And notice where it happens. So see how there's a 0 right here at maybe like -2/3, and then a 0 slope here at like 2/3. And I can see that that matches up with where my derivative graph goes through the x-axis. And if I look at the other graph that I have remaining, this graph goes through the x-axis 3 times. And I only have 2 places of horizontal tangency on graph C. So the answer is going to be C, is going to match up with the second graph here. But let's continue to analyze the slopes so we can learn how we would deduce this. Between these 2 horizontal tangent lines, if I thought about, let's just pick one value and draw a little tangent line, that slope there is a negative slope. So that means between those 2 x-intercepts, I'm going to have to be below the x-axis on the graph of the derivative. And notice that between these 2 zeros here, I'm below the x-axis, so my slopes are negative. And then if I pick any place to the left of this first horizontal tangent line, all of these slopes are going to be positive. And then over here, so let's draw little pluses. And then over here, all my slopes are going to be positive as well. So to the right of my x-intercept and to the left of this x-intercept, I'm going to have to be positive above the x-axis. So notice that I am positive above the x-axis to the left of this 0 and to the right of this 0. So that matches what's happening on our correct answer, our correct choice, the second graph in the second row. So then finally, we'll just justify why option D does go with this last one. So we know that it's the only one left over. And we can again think about those horizontal tangent lines. So we can see that there's these curved minimum and maximum values, and there are 3. So there's a maximum and there's a local maximum. And here's a local minimum. They're not sharp turns. So each of those has a horizontal tangent line or a slope of 0. So we can see that our graph here has 3 places where I cross the x-axis, so -1, 1, and 1, and we can see that that matches up, -1, 0, and 1 for my slopes. And then I can think about just drawing some little tangent lines and confirming the rest of the graph matches. So here I'd have positive slope to the left of this first 0, and here we go, to the left of this first 0, I'm above the x-axis. And then for between -1 and 0, well, now I have negative slope. If I were to draw a tangent line, I have negative slope. So between -1 and 0, I'm below the x-axis. And then from 0 to 1, if I draw a tangent line, I have positive slope just between 0 and 1. So here I am above the x-axis, positive slope. And then over here, now I have some negative slope. So I need to be below the x-axis once I cross that 0 value, that horizontal tangency point at 1. So this is the type of thing that we're going to get better at as we practice, and you don't have to draw all the pluses and minuses and the zeros, but as we're just starting out, I would say that it's the best technique to match the original function, so these on top are the original function, to their derivatives, or the slopes of tangent lines graph. Alright, let's go ahead and do an AP matching one. The graph of f is shown in the figure, so this graph right here is f of x, and which of the following could be the graph of the derivative of f? Sorry for the weird gap. So this is the graph of f, and all of these are potential graphs of the derivative. So which one is actually the derivative? So we'll go ahead and use the strategy we took a look at before, which is we definitely know there is a horizontal tangent line right about here. So that slope is 0. So somewhere like a little bit after, to the right of 0, I'm going to have to go through the x-axis on the graph of my derivative. So let's use that to start eliminating. So I can eliminate this graph, right, because way over here is when I touch the x-axis, so that's not it. Same thing with this one, so option D, way over here is when I go through the x-axis. It'd be held closer to right about here. So I can see that that happens in graph A, in graph C, and in graph E. So now we're going to have to do some analyzing of other slopes. So let's go ahead and start over here off to the left. So right here, maybe if this graph continued, we might think that there's actually another horizontal tangent line. We don't know for sure, but right here, right here, if I were to draw a tangent line, that slope is positive, but it's very small positive, right? It's almost close to 0. And then as I move along, I'd still have positive slope, and it's getting bigger right here, but then as I get closer to over here, so if I drew a tangent line like right here, it's smaller and positive again. So to the left of my 0, my x-intercept, I have to be above the x-axis. So let's look at A. Well, A to the left of this 0 is above the x-axis, so that's still a contender. But C is below the x-axis, so C is out. And if I look at E, well, E is above the x-axis, or E is positive, to the left of that 0 location where I had a horizontal tangent line. So now it's between A and E. And the answer is going to rest in what I started to say as I started on the far left over here, that it's almost like if I were to continue this, I might think that it has another minimum. It has another place of horizontal tangency that's like 0. So this graph E here, the slope is just more and more and more positive. But over here, the slope looks like it was getting closer to 0. So as I look at graph A, right here off to the left, right where A is, it looks pretty close to the x-axis, and that's because maybe it ends up being 0 again. We're not sure, but the idea is that the slope was small and positive, then it gets bigger and positive, right? So let's make like a big plus right here, and then it gets small and positive again. So small and positive, and then bigger positive, and then small and positive again, and then the slope is 0. And then over here we can see that our slopes are going to be negative, really negative, and then kind of negative again. So here I get closer to potentially hitting the x-axis again, because it looks sort of like I might have another horizontal tangent line if I were to continue this graph. So the answer here is going to be A. So not E, because the slopes just keep getting more and more positive here. And here the slopes were positive and kind of flat, and then steeper, so more positive, and then less positive, so kind of flat again. Alright, I'm really sorry about the blurriness of this. I hope it's clearer on your page. Once again, we have the graph of a function f is shown. That's this graph here. Which of the following could be the graph of the derivative of f? So this one's pretty similar to one we did previously while matching. So if we start with thinking about those horizontal tangent line locations, we're going to have a horizontal tangent line right here. So we're going to have a slope of 0 and a slope of 0, right around here, one to the left and one to the right of 0, 0. So as I look at my graphs, well, this one doesn't cut it, right? This one goes to the x-axis at 0, and I don't have a slope of 0 at 0. So can't be A. This one's a contender, right? So I go through the x-axis twice, a little bit to the left and a little bit to the right of the x-axis. This one is not, right? So this one does not have, two places here and here where I cross the x-axis, so that's out. This one is a contender, right? Because I go through the x-axis twice, and this one doesn't go through the x-axis at all, so that one's out. So we're really just looking at B and D here, and if we just pick one point, so how about we pick 0, and we analyze the slope of the tangent line. So that slope is negative. Hope you said it before, I did. So that slope is negative, which means on the graph of the derivative, I would need to be below the x-axis. So the only one that satisfies that is option B. So in option D, I'm above the x-axis between my two horizontal tangent lines, so it cannot be that one. Alright, so we want to find derivatives graphically given f of x. So this function here is my function f of x, and although I said we are going to be dealing with curves, it's easiest to start out with lines. So this here is my graph of f of x, and what I want to draw is the graph of f prime of x. So f of x is some function, and f prime of x is going to be some function as well. And since f of x is defined for values between, let's see, -6 it looks like, and 8, what I'm going to do is I'm going to draw myself an xy coordinate plane from -6 to -8. So this is just going to be a little rough sketch here. So 2, 4, 6, 8. -2, -4, and -6. Alright, so over here on the graph of f of x, all the way from, let's say that this function does keep going on forever over here. So from -infinity all the way up to 0, but not including 0, I am this linear function here that I can find exactly. It's the function -x. So this linear function right here, -x, has slope -1. So for any value from -infinity all the way up to 0, the derivative is always going to be -1. So on the derivative graph over here, the derivative graph anywhere from -infinity all the way up to 0 is going to be -1. So I'm going to draw my graph over here in blue. So from -infinity all the way up to 1, the derivative is always -1. So if I read this derivative function and I ask you, well, what's the derivative of the original function f at -4? You go to this function and you say, well, it's going to be -1. In fact, for any value to the left of 0, the derivative, or the slope of the tangent line, or in this case just the slope of the line, is -1. Well, let's analyze what's going on exactly at 0. At 0, I have this point of discontinuity, right? I have a removable point of discontinuity. And if a function is discontinuous, it cannot be differentiable. So there's no derivative at the x value of 0. So over here, right here along the y-axis at an x value of 0, I have to make sure that there is no derivative value. So I have to be undefined on the graph of the derivative. So now I can keep going. What about between 0 and 2? Between 0 and 2, this original function is the linear function x. So I can see it has rise over run of 1, so up 1 over 1. So I have the line x, and the derivative of x is just 1, the slope of the line. So this is 1x. So between 0 and 2, I need to be up at a y value of 1. So I'm going to go ahead and draw that as a horizontal line. So I have to be 1 between 0 and 2. And again, at 0, I have to be undefined, so I have to have this open circle there. And at 2, you'll notice that I'm not defined there, so I can't be continuous there. So also at 2, I'm going to have an open circle. And if you notice even closer, between 2 and 3, there are no function values at all. There are no function values. So between 2 all the way up to 3, I cannot be continuous because there's no limit from the left over here and there's no function values in the middle. So from 2 to 3, if I'm not continuous or even defined, I can't have a derivative at those locations. So from 2 to 3, there's going to be a gap. There's not going to be anything there. So if there's no values, there's no limits, there's no continuity, that means there's no derivative. So I have to just skip all the values from 2 to 3, and that includes at 3. So there can't be a derivative right here at 3, right? There's not even a left part to the function. But picking up from 3 onward, let's say this goes all the way to infinity, this is a horizontal line. So this is the horizontal line at 1, so this is the function, y equals 1 from 3 to infinity, and the derivative of a constant function is 0. So from 3 onward, right, so I should have been careful, I shouldn't put the circle up here, the circle should actually be down here, because from 3 onward, I have a derivative that is going to be 0. It's going to be on the x-axis. So this graph here represents my derivative at any point. So in other words, let's imagine that we were not given this function over here. I've never seen this before in my life, but I've been given this function here, f of x, and I'm asked questions about f, the original function. So I'm asked about its derivative. So what is f prime of 1/2? So assuming I don't even know what f looks like, but if I know f prime of x, well, 1/2 would be about right here. So if I read this graph that I've drawn, at 1/2, the derivative is 1. So f prime of 1/2 is 1. What about f prime of 6? So at a value of 6, this function is 0. It's this constant piece of the line. So f prime of 6 is 0 along the x-axis. So it's a little bit tricky, but if we break it down piece by piece and we remember that the derivative is the slope of the tangent line, what I've drawn here, f prime of x, is the slopes of the tangent line, or the lines of this original piecewise function. Alright, so let's take a look at another example. So I have another piecewise function here, and I'm going to go ahead and draw myself an xy plane so that I can draw the derivative of this piecewise function. So this is the function f of x, and we'll go ahead and say that down here it continues on forever, but that it does stop right here at 2. So over here I need to stop at 2, and then I will go ahead and mark up a bunch of values over here, but it is going to go on forever. And here's 0 and 1. Alright, so let's go ahead and start over here where we have this piecewise function where this piece is linear. So this linear function, if I were to try to draw f prime of x, well, this linear function goes from negative infinity up to 1, so I know that's where I'm going to have to stop right now. And I'm going to draw a line that represents the slope of this line. So I'm going to draw a constant line at the slope of this linear function here. So if I pick a point on this line and I try to determine rise over run, so this point here, this is -1. So here I'm at -3, -1. I'm going to go up 1, and I'm going to go over 1 to get to the point. So this line has slope 1. So up 1, over 1. So from negative infinity, way over here, up to this x value of 1, that's when I stop having a slope of 1. So 1 on the y-axis, I'm going to have this horizontal line at 1 all the way up until this value here at -1, where there's this sharp turn happening. There's a corner. And at a corner, I have a place of non-differentiability. So on the graph of the derivative, there's going to have to be an open circle there. Alright, so now let's go ahead and analyze what's happening between -1 and 0. Between -1 and 0, if I think about drawing a tangent line, because I no longer have a linear function, so I can't say that for every point between -1 and 0, the derivative is always a particular number. But what I can say is that if I draw a bunch of tangent lines, so little tiny tangent lines at different points, what I know about the slopes of each of those lines is that the slope is negative. So what that means is that on the graph of f prime of x, negative values happen down here, right? Happen below the x-axis. So between -1 and 0, so right here, I know that I'm going to need to be below the x-axis. Whoops. So let me erase just the little red part. So I know between -1 and 0, I'm going to have to be below the x-axis. All right, really close to -1, if I think about drawing a tangent line, that tangent line is going to have a pretty steep negative slope. So let's say it goes, let's say down 3 and right 1. So it has a slope of -3. So right at -1, or really close to -1, it has a slope at -3. So remember, we're drawing a sketch. So what's happening then is I move closer to 0, the slope of that line, so I'll kind of remove it. I have this steep slope, and then not so steep, and then a little flatter. And so you can see that the slopes are going to be getting closer and closer to horizontal lines. So the slopes are going to be -3, but then this one might be, down 2 over 1. So this one might be -2, that one was -3, then -1. And it's going to get closer and closer to 0 as I approach 0, because right at 0, I would have a perfectly horizontal tangent line. So at 0 on the derivative, I would be on the x-axis. But from -1 to 0, my values are pretty steep and negative, so -3, and then they end up getting closer to 0. So I can sketch this graph to look something like this. So first they're -3, then they're getting closer to -2, -1. Ultimately, they're going towards 0. And then picking up at 0 again, up to 2, if we analyze what's happening to the slope, so let's try a different color. Let's try black. So right after 0, I'm going to have a not so steep slope. And as I continue to move closer to 2, the slopes are getting bigger and bigger. So this slope might have been, let's say, 1/2, and then 1, and then 2, and then 5. So these values are getting more positive. So if at first, right here, I'd be 1/2, and then 1, and then at 2, I go all the way up to, we said, 5. So now my slope of the line, my slopes of tangent lines are getting bigger, and they're positive, so I need to be above the x-axis. But right at 5, I made a mistake. Or sorry, right at 2, I made a mistake, because at this point here, I don't have a limit from the left and a limit from the right, so I can't be continuous. If I'm discontinuous, I'm non-differentiable, so I needed to end that at an open circle. And then this would continue left forever if this went down forever, so this would be a sketch of my derivative of this function. Now, again, the points here are vague, so I just chose 5 and I chose -3, but again, it's just a sketch of the graph. So as long as, if you choose -3, as long as your values are getting closer to 0 as you move from left to right, from -1 to 0, then your sketch is accurate. Alright, so now we have one more example. Let's go ahead and start this time off to the right where I have a linear function. So again, here's my f of x, just to label everything. Here's my f prime of x that I'm trying to draw. Starting at 1, from 1 to 3, and we'll say that this goes on and on forever. So 1, 2, 3. Starting at 1, well, at 1, I have this jump discontinuity, so I cannot be differentiable, so I'm going to have a hole at 1. But from 1 on, I have a linear function, so the derivative is going to be the slope of this line. Well, here on this function, we're actually given the line. It's 6 minus x. So that means that the slope of this line is -1. So from 1 to infinity, the derivative is -1. So the derivative graph is going to be down here. At 1, it's no derivative, so I have to be undefined. And then all the way to infinity, I'm going to be the value -1. So now, here's where I have to do a little bit of a sketch, because now I have a curve. Well, let's mark the one value we're sure of. Right here at 0, I'm going to have a horizontal tangent line. So at 0, a horizontal tangent line means that the slope is 0. So at 0, I'm going to mark the point 0 on the graph of the derivative. And then I have to interpret what's happening between 0 and 1, and then from negative infinity to 0. So from 0 to 1, let me go ahead and erase this little horizontal line so we can sort of interpret it. So right to the right of 0, if I were to draw a little tiny tangent line, it's going to have a slope of something like, again approximating, 1/8. Not a very steep slope. And as I continue to move along, I'm going to have steeper and steeper slopes. So maybe 1/4, and then 1/2, and then 1. So what I'm saying is that right before I get to 1, I had a slope of 1. So right before I get to the x value of 1, I would have a slope of 1. But right at 1, we agreed I cannot have a point on the graph of the derivative. It has to be undefined. And then starting at 0, it's a small number like 1/8, and then 1/4, and then 1/2. So if I connect that as a line, and again, it's just a sketch, then I'm going to have that my derivative graph between 0 and 1 looks like this line, where the slopes are getting bigger. They're all positive because, again, if we drew little tangent lines, each of these lines has positive slope. And then over here, off to the left, if I were to think about the different tangent lines, so way over here, if I drew a tangent line, that's a pretty steep slope. And then as I continue to move along, my slopes are getting less and less steep, so they're getting flatter. In fact, they're getting closer and closer to being horizontal, where horizontal lines have slope 0. So they start out to be big negative values. So each of these lines has negative slope. So we'd go down and to the right, down and to the right. So this would be some negative slope, like, I don't know, again, we're making up values here, but we'll go ahead and say -6, and then maybe -4, and then -3, -2, -1, -1/2, -1/4. So these values are below the x-axis on the graph of the derivative. Negative values, again, live down here. So let's go to -6. So that's where we said was maybe at about -3. So again, just in our sketch. So we had -6, and then, -3, and -2, -1. So it's like this linear function down here where the values are getting more and more negative because the slopes are getting steeper and steeper. So if I continue this curve, I would get a very, very steep slope where the line would start to look vertical. Of course, it would never get vertical, but it would start to look vertical. So this is going to be a sketch of my derivative graph. So again, if I were to ask you for f prime of -3, so tell me on the original function f of x about the slope of the tangent line at -3. I could look at this graph and say, well, here's -3. I have to go to my derivative where it's close to -6. So what that means is that on the original function, the slope of the tangent line was about -6. So that's how we read the graph of the derivative. But more importantly, how we'd go from a sketch of the original function and reading its slopes to sketching the graph of the derivative.